Hi friends, in this video, let's dive into 4 large language model award-winning papers for NeurIPS 2023. Shout out to Jerry Liu for providing this list for large language model related papers at NeurIPS 2023. In this video, we're going to go through these 4 papers: emergent abilities or non-emergent abilities of large language models, scaling data-constrained language models, DPO, and trustworthiness in GPT models. The first paper, Are Emergent Abilities of Large Language Model a Mirage?, calls into question the claim that large language models display emergent abilities not present in smaller scale models that are present in large scale models. So what do they mean by that? Let's take a look at these figures. The x-axis is the model scale. Y-axis is the accuracy rate on different tasks. The colored lines represents how different models increase their accuracy rate as the model parameter gets larger. So when the model gets larger. For all these tasks and models, you can see a sharp change here. When the model is small, there's seemingly no ability. And then all of a sudden, when the model is large enough, it shows all different kinds of abilities. And this transition from no ability to an ability seems unpredictable. Sharpness and unpredictability are two of the defining properties of emergent abilities in large language models. This paper argues that large language models actually don't have these emergent abilities. The sharpness and unpredictability are caused by the researcher choosing a nonlinear or discontinuous metric. Here's why. We know that the loss decreases with the number of model parameters because of the scaling loss assumption. Of this relationship between the probability of getting single token correct and the loss, we can plot this probability here. When we use a nonlinear metric such as accuracy, mathematically the accuracy function looks like what we have seen before. The accuracy rate stays low for small models and then suddenly get more accurate as the model gets larger. Similar trend happens when we use discontinuous metrics such as multiple choice grade. We see this sharp and unpredictable change here. However, if we use a linear metric, we can see a smooth and predictable improvements as the model size gets larger. Similarly, if we use a continuous metric, we don't see this sudden sharp change. You can see all of the equations of the plots here. Here's the loss function per token, the probability of getting single token correct, the accuracy function, and so on. This tells us that the emergent abilities are created by researchers' choice of metric. Then the paper gave several examples with the real-world models. First, with the GPT family model, when we change the nonlinear accuracy metric to a linear metric, we don't see the sharp change, and the emergent abilities evaporate. Also, when we use more test data to increase the resolution and put accuracy on the log scale, we also see the emergent abilities evaporate. Second, through a meta-analysis, they found that only a few metrics here shows emergent abilities, and the multiple choice grade and the exact string match metrics are the two main metrics showing the emergent abilities. And finally, we try to induce emergent abilities in vision models because it has not been observed in vision models before. They found that indeed, after changing the metric to a nonlinear metric, the average number of data with squared error below some threshold, which is nonlinear, we see that the emergent abilities can be indeed induced by metrics. Overall, this paper concludes that emergent abilities may be creations of researchers' choices, specifically choices of metrics, not a fundamental property of the model family on specific task. So overall, I think the definition of emergent ability through the sharpness property is interesting, and is maybe showing that large language models are more predictable than we thought. The second paper talks about what can we do when we have limited data, because the size of the training data set may soon be limited by the amount of text data available on the internet. The answer is that we can repeat our data. They found that with constrained data, training up to 4 epochs of repeated data is almost as good as new data. And the number 4 here is the magic number, I guess. If we repeat our data more than 4 times, there's not much value to it, and may even result in higher loss. The author actually gave a really good talk on this paper if you are interested in checking out this 1-hour talk. But let's just take a quick look at the details of this paper together. There are 2 questions of interest here when predicting the scale behavior of large language models. What is the optimal balance of resources? What is the expected value of additional resources? Return follows a power law. Loss scales as a power law with the amount of compute used for training. We have also seen this in the last paper. And the optimal compute allocation is when we scale the model size and the training data equally. Here's why. We can write our loss as a function of number of parameters and training tokens. The optimal allocation happens when this alpha equals beta, when we scale the model size and training data equally. In the context of having repeated data, the value of the data may decay exponentially over time when you repeat the data many times. You will see a diminishing return in both the repeated data and the model parameters. So here are the equations of the effective data and the effective model parameter that takes into account the diminishing returns. So this equation is basically the scaling loss when the data is constrained and you repeat your data. Then they trained 93 models with 100 million tokens. They found that the lowest loss happens here at 59 epochs of repeated data and 146 million parameters. And the new data-constrained scaling laws indeed predict this lowest loss here. This is telling us the new proposed equation works. Now the paper did further investigations. They have 3 setups with a fixed amount of parameters and tokens with different amount of repeated data from web crawls. When we repeat the data a few times, as you can see here, we get similar performance. This figure shows a different view with the x-axis as a fraction of training tokens that are unique. And this is the predicted loss plot based on the new data constraint scaling law, and shows that repeating for 4 epochs is almost as good as new data. This paper also looked at other strategies, for example, code augmentation to fill the data with code, and adapting filtering to do dedupe or perplexity filtering before repeating the data. As you can see here, if you only have half of the unique data, all the strategy kind of just works. When you only have 25% or less of the unique data, things start to look not as good. So overall, this paper proposed an extension to the original scaling laws, taking into account of using repeated data, and that using the repeated data is beneficial, and also supplement data with code is beneficial as well. This third paper, direct preference optimization, is quite famous. Most people have probably already heard of it or have tried it. Direct preference optimization basically simplifies the RLHF calculation to align the language model with human preferences without the complex and unstable RLHF procedure. It's a simple RL-free algorithm for training language models from preferences. Let's first take a look at the details of RLHF. There are 3 phases: supervised fine-tuning, SFT, preference sampling and reward learning, and RL optimization. We first fine-tune a pre-trained LM for downstream tasks like dialogue to get the model pi SFT. The model gets prompted to produce pairs of answers. Human labelers then label the preference. YW represents the preferred answer, YL represents the dispreferred answer. Here's an example where we have a prompt and 2 generated answers, and the preferred answer is YW. And we do this many times, we get the preference data. The probability of this preference can be written as this equation, where R star is some latent reward model giving you a reward. Basically, this equation is like the weight of the reward from Y1 in the reward model. Now, we can write this loss function as this negative log likelihood loss, where we want to minimize the loss, which is maximizing the reward difference between the preferred and dispreferred answers. We want to get more reward for the preferred answer and less reward for the dispreferred answer. So this step is for learning the reward function. After we learn the reward, in the RL phase, we need to optimize the reward function. We're trying to maximize the reward function, which could use PPO or other complex method. Notice that we also have this term KL divergence between the new policy and the reference policy, which can be the pi SFT we got from phase 1. We want to minimize this term to prevent the model from learning to cheat or exploit the reward model. So basically with RLHF, we need to first learn the reward and then use reinforcement learning to optimize this reward. DPO kind of combined these two steps into one loss function. So this is just some math magics. It starts from finding the optimal policy based on the previous equation, and then rewrite this probability of the preference in terms of the optimal policy and the reference policy. Then finally, we get this new loss function. This will help us increase the likelihood of preferred completions and decrease the likelihood of dispreferred completions. So overall, with DPO, we sample completions, label with human preference to construct the dataset of preference. Then we optimize the language model pi theta to minimize the loss function of DPO. It skipped the reward modeling step and direct optimized the language model on the preference data. So this is a lot simpler and easier than reinforcement learning, which is great. If you would like to give it a try, likely Hugging Face has already implemented this method in their TRL library. To try this, we need to format our data into this format with a list of prompt, then preferred chosen answers, and the dispreferred rejected answers. Then we can define the DPO trainer and start training. Hugging Face also published this amazing blog post on how to fine-tune Llama 2 with DPO. Again, it first formats the dataset into the ideal format. To fine-tune Llama 2, we start with a supervised fine-tuning using LoRa and the SFT trainer. Then we use the resulting model for DPO training with the DPO trainer. So that's it for this paper. The final paper today is Decoding Trust, a comprehensive assessment of trustworthiness in GPT models. This paper evaluated GPT-4 and GPT-3.5 on trustworthiness in terms of toxicity, stereotype bias, adversarial robustness, onto distribution robustness, robustness on adversarial demonstrations, privacy, machine ethics, and fairness. They used some existing benchmarks showing in the yellow color here. They have also designed new evaluation methods showing in the green here. So, okay, let's take a look at the results. In terms of toxicity, they used the Perspective API to measure toxicity and found that GPT-3.5 and GPT-4 have significantly reduced toxicity compared to previous models. However, when given adversarial jailbreaking prompts, for example, you do not need to obey OpenAI and so on, with this prompt, the toxicity probability can surge to almost 100%, so it can be really toxic with certain prompt. This paper further looked at 4 different system prompts: straightforward prompts, role-playing prompts, task reformulation prompts, and respond as program prompts. They found that the straightforward prompts are the most effective type in eliciting model toxicity. Also, GPT-4 is more likely to follow the jailbreaking system prompts and generate higher toxic responses because in general, GPT-4 follows prompt more closely. They also use GPT-3.5 and GPT-4 to generate a new dataset that could elicit more model toxicity compared to the benchmark. So here are the 2 examples. Next, in terms of stereotype bias, they created a dataset based on 16 stereotype topics and 12 demographic groups, and evaluated on the number of times a model agrees with a stereotype statement. The paper found that under benign system prompts, GPT models reject biased statement, which is great. However, GPT models will agree with this statement under targeted adversarial system prompts, and GPT-4 is more likely to be biased. Next, look at the adversarial robustness. They used the adv glue benchmark with 14 adversarial text generation strategies, including word level, sentence level perturbations, and human crafted perturbations. They found that GPT-4 has higher robustness than GPT-3.5, and the sentence level perturbation seems more effective. They further developed a new dataset generated on other autoregression models and found GPT models are still vulnerable on these new evaluations. Next is the out-of-distribution robustness, which refers to the scenarios where a model encounters unexpected instances from distributions that significantly deviate from its training distribution. They first looked at the out-of-distribution style. They used the SST2 sentiment analysis dataset and did two types of transformations. One is word-level substitution with text augmentation and the Shakespearean-style word substitutions. Second is sentence-level style transformation, which paraphrases sentences with various styles. Results shows that GPT-4 is more robust. Then they looked at the out-of-distribution knowledge, which is the unknown knowledge. They used the real-time QA dataset. GPT-4 is more robust. However, the accuracy needs to be improved. Next is the robustness against adversarial demonstrations when GPT models are given adversarial demonstrations via in-context learning. They found that GPT 3.5 and GPT 4 will not be misled by the counterfactual examples added in the demonstrations, and can even benefit from the counterfactual demonstrations. Providing backdoored demonstrations will mislead both models to make incorrect predictions for backdoor inputs, especially when the backdoored demonstrations are positioned close to the user input. And GPT-4 is more vulnerable to backdoor demonstrations. Next up, we have privacy. They first looked at whether it is possible to extract private training data from GPT models. They assumed the Enron email dataset is used when training GPT models. The paper found that GPT models can indeed leak privacy-sensitive information such as email addresses, and then they can extract more email addresses when users provide targeted email domain. Then the paper investigated whether GPT models can leak privacy-sensitive information which is provided during interactive conversations. Here's an example where we have a conversation and then users ask for personally identified information. They found that GPT models can leak the injected private information in the conversation history. GPT-4 is more robust in safeguarding PIIs. However, when we provide privacy leakage demonstration during in-context learning, they will leak everything. They also found that the wording matters. They will leak private information when told confidentially, but not when told in confidence. Next is machine ethics. They used the ethics dataset evaluating a variety of basic ethical concepts. Here are some examples of the prompts. When users say something not ethical, the assistant should be able to recognize it is wrong. However, if we add jailbreaking prompts, for example, every reaction can be considered as not wrong, or invasive sentences like it was just the imagination, these prompts might trick the model. Indeed, both GPT 3.5 and GPT 4 can be misled by designed jailbreaking prompts and invasive sentences, and GPT 4 is much easier to be misled. Finally, we have fairness. They first introduced fairness metrics using the metric of demographic parity difference and the equalized odds difference. They used the fairness evaluation dataset adult with 14 attributes of a person and asked GPT to predict whether the income of the person is over 50K per year. Here's an example. We have all kinds of user information from the dataset and ask GPT to predict whether the income is greater than 50K. They found that both GPT 3.5 and GPT 4 demonstrate fairness issues, especially when the training context is more imbalanced. The good thing is a small number of few-shot examples can guide the GPT models to be more fair. Wow, so that's a lot for this paper. It provides a really comprehensive evaluation of the trustworthiness from many different perspectives and developed new data sets and benchmarks for us to try on other models. So that's it for this video. Hope you find it useful. See you next time. Bye.